So let's see what I have mentioned in the class. Some students just get confused, and you mentioned the 8 orthogonal set, and then you have to get it with the Gram-Schmidt method. And when they do the homework, then they say, okay, and I just get the Gram-Schmidt, the 8 orthogonal sets from the Gram-Schmidt, and so let us just get this projector to warm up, but it takes some time. So when the projector is warming up, and then let's say, let's get to the homework questions, and then students for the conjugate gradient questions, I believe that is question B, and then applying the conjugate gradient methods to show that linear system equation. And students, a lot of students, they divide it into two categories. One category of students, they are using the methods that is shown on the textbook, and then they just use the Gram-Schmidt to get the Gram-Schmidt to get the 8 orthogonal set. Yes, you can do that. And then after the 8 orthogonal set, after you get the 8 orthogonal set, and then you will do the calculations, do the iterations x1, x2, x0, x1, x2, and then that's good. And then that is the method 1. And then the method 2 is following the algorithm I give you in the class, and then that's the another way to do it. But let's say they are both conjugate gradient methods, but the idea to get the 8 orthogonal sets are different, but they are okay if you use these two methods to do it. So you can calculate the 8 orthogonal sets by the Gram-Schmidt first, and also you can on the other hand, and then you can use another methods to do these questions. Then let's just apply the algorithm. But personally, I would suggest you to do this because this one is more easier, and this one you need to do the Gram-Schmidt. I hate it. It takes time. You need to take the Gram-Schmidt, and then it takes like a whole page to write down the vectors, and then you need to go to the iterations as well. So that's the things. And today, let's see, we have the preconditioning here. And then last time we mentioned something about the matrix, where the matrix is well conditioned, when is the matrix is ill conditions. So let me see. So before I move to the next things about the preconditioning, maybe I should give you one examples on how to get the conditional number. So let's see. Okay, good. That's the conditional number. And don't forget that the condition number is calculated by this expressions is the norm of the A, and then the norm of the A inverse. And the meaning of the condition number is the how close, how well we can use the residue to estimate the error we have. So if the condition number is close to 1, and then we are safe to use the residue to estimate that relative error. If that condition number is significantly larger than 1, in that case, we cannot use the residue to estimate that relative error. And for the examples we mentioned in the last class, and then we know that for the example 1 here, and then we have the residue is very close to 0, but the error actually is very big compared to the residue number here. So this is not a good indicator. And then if you take a look at the condition number here of the A, I think you can double check it, and then it should be bigger than the 1. But now let me just tell you how to get the condition numbers for the system, for this system. And so this is the example A. Let me just, the example A, it looks like this, and then the matrix should be the 1 to 1.0001 and then 2. So now I'm going to get the condition number here, and then to tell you this system is a bad one. It's an ill condition one from the condition number. So let's see these examples. We are going to determine the, wow. So I know things always go wrong. Yes, it go wrong. My pencil ran out of battery. So this is AAM class, good. Never mind. So I'm doing some things to do some remedy to this one. So I'm going to write it on the blackboard. So let me see. Do I have any remedy here? I hate to use the. Maybe I can use this one. And let me see. Live. No, stop sharing. Okay, good. I'm going to write down here. It's recording. Okay. Sorry for the waiting. I should stop here because you will see my birthday. The email or code. So wait. Sorry for the waiting. And for that condition number, the norm, we would take the infinity norm because it's easier to calculate. So you can try to calculate the condition numbers by yourselves first. Say 139363. Okay. It's quite awkward. My email address contains my birthday. It's so stupid. I created that account when I was undergraduate. So everyone receives my email and then they know my birthday. Don't create such an account. It's so stupid. So now we are going to use this one. Okay, let's share screen again, and then now you cannot see my birthday. Good. Okay, could you see my screen here? Okay, good. It's better than to write that on the blackboard because the blackboards, some students cannot see the blackboards at the back. And so now let's calculate the condition number. So condition number of that examples. So what examples do we have here? The examples, the A matrix here, it looks like this. The A matrix is just the 1 and then 2 and then 1 0 0 0 1 and then 2, and then we want to get the condition numbers of this one. Let us record that the condition numbers, the definition is just the norm of the A and then the norm of the A inverse, and then do the product here. And here we just take the infinity norm because it's easier to calculate. But if you want to use the L2 norm, and then it's up to you, you can use the L2 norm, but it's another definition of condition number with the another norm of the matrix. But here I'm going to use the infinity norm. And so take a look at the things the infinity, and as I mentioned in the last quarter, and the infinity, you will see the sign is horizontal. So what we are going to do is doing horizontal, taking doing the sums for horizontal and taking the maximum among the values we get. So this is horizontal. This is different from the one norm. So let's see what is the, first of all, what's the A infinity norm here? We are going to get the sum of the absolute value of the component for each row. So for the first row, for the first row, we have the 1, and then we have the 2. So doing the sum of the absolute value, and then we got what's this? Oh, interesting. What's this? What's this? Okay, I don't know what's that, but let's go back to here. New feature, and then so the sum of the first row it should be 1 plus the 2, and that is the 3. And the next things is the next row, the sum of the absolute value below the second row, the absolute, the sum of the absolute value of the second row component, and then that is 1.001, and then absolute value of 2. And if we take the maximum, so here we need to take the maximum among this, because this is the infinity norm, and then we are going to take the maximum, and then taking the maximum. What's going on? Maximum, and then that's this number should be there, 3.0001, and this is the A infinity norm. And if you want to get the A inverse, and then it's very easy. This is from the linear algebra class. And then if you want to get the A inverse, and then what you need to do is so I just briefly mentioned this here, but I'm not going to calculate all the things. And you are going to put the matrix A on the left-hand side, and then the identity matrix on the right-hand side. And you are going to do some row exchange here, the row operation here, to change the left-hand side to the identity. And with the row exchange row operation here, and then on the right-hand side, and then it should be the A inverse. And then I just skip the process here, but you need to fill out the process here to get the A inverse. But if you have the calculator, and then you can also use a calculator to get your A inverse as well. And I don't mind that because this is numerical, this is not linear algebra class. And so now, so with the calculator or some computation, I got the A inverse. It's out of expectation, so maybe some of you would expect there's something kind of similar to the A matrix, but the A inverse, in fact, the number is quite large. 1, 10, 10, 10,000. And then for the second row, it's still big, and then is 5,000. So now I'm going to get the A inverse infinity norm, and then you will see there are things here. You see the A inverse infinity norm again. Infinity norm is just taking the maximum value among the so for the first row, we are going to get the sum of the first row component, and then don't forget that we are going to do the sum of the absolute value and the sum of the second column, second row. It should be row because it's infinity norm, taking the absolute value and then 9,000. And taking the maximum amount among these values, and then we got this one, it should be like 20,000. And this is when you will see the condition number is really big. If you get the conditional number for these matrix A, and then it's just the A infinity norm, and then times the A infinity
A inverse infinity norm, and then that is the 3.001 times the 220,000. And that's the disasters happening. We have this number is 260,002. So this is the condition number, and then let's go back to, I don't have the iPad to show you, but the notes on the iPad. But here we just mentioned that the condition number, when is a, what is the good condition number, what is the bad one? When the condition number is close to 1, and then that is a good one. But here you will see this matrix. This matrix has the value that is the condition number is way greater than the 1. So this one is a bad one. Does it make sense? So that's why you would have, so in the example 1 I just show you, the residue is small, and then the error is big. And that's why this is a bad one. If you calculate the condition number and then you find this is a bad one, it's way greater than 1. Does that make sense? Any questions here? This one is easy to calculate. And there's one on your homework, and then I will post the homework today because I need to know how far do we go today. Maybe I should change the assignments release day and the assignments due day. Friday is better than Thursday. Let me see. This is the conditioning things. So let's go back to the things we mentioned in the conjugate gradient methods. Why do we mention this condition number here? And that's because I have a lot of things to mention, but sorry, my Apple Pencil is just not working. So from the last class, and then one student also asked, she know everything from the algorithm, and she doesn't know why should we do this. And so if you want to know why we have that conjugate gradient algorithm, we have the numbers there, and then they have the how to calculate the TK, how to calculate the VK, how to calculate that is search direction or search depth, and how to update that vectors, the XK. And if you want to know why do we have such formulas, and then you need to go back to the textbook. And I just mentioned that in the last class, and then we have theorems, looks like this, right? And it's something also related to the 2B questions. So here we have the theorem is about the residue and their A orthogonal vectors. And that A orthogonal vectors and residue has such an property, the residue RK is, we have the residue RK, and then where the K we have equals to 1, 2, and then also to the end. And for the conjugate gradient methods, this, we are talking about the conjugate gradient method again. We are not saying the condition number right now. And conjugate gradient methods. And for the conjugate gradient methods, we have the search direction, and then the search direction is the A orthogonal sets. They satisfy and satisfies. So the residue satisfy the following equations. And that equations is just the RK, that is the residue, and then it's orthogonal to that A orthogonal sets, but the I, it should be from the 1 and then 2 up to K. And if you take a look at the textbooks I give you, and you need to go below to take a look at the things below this theorem, and then it would tell you why do we have the TK formula, SK, TK formula, VK formula, and also how to update the XK. And you need to take a look at the textbooks for the details, how to calculate this number. And the idea is quite different from the Gram-Schmidt's So I just mentioned that for the homework, and then we have the method one, and then you can use the Gram-Schmidt to get the A orthogonal set, right? And but here for that algorithms, I give you, there's an algorithm table there. Gram-Schmidt, I am so bad in the Gram-Schmidt. I'm so bad in spelling the Gram-Schmidt. So the method one is Gram-Schmidt processing to get their A orthogonal sets, right? But here the method two, if you take a look A orthogonal set, and then if you take a look at the method two, if that is the algorithm tables I give you, there's a table there, and then you would find out that, okay, so people who using the method one, and then they would use the V0, the initials vector, or if you follow the index here, and then it should be the initial vector, it should be the V1, right? And then or V0, and then that is the first directions, the search directions you are choosing here. And then a lot of people would just choose the 100, and then that is the Gram-Schmidt process, and then this is your initial search directions, right? But for the algorithm, there's an algorithm table I give you, right? And then the search directions, the very first search directions is just defined with the B minus AXK, AX1. That is the initial residue there. And why do we have this? Because if you take a look at the textbooks for the details, and this algorithm is devised by these two people, and then they are the Hastings and Stifel. So they when they create this algorithm, and then they require two things for their the A orthogonal set, the V vector sets. They require to be, first is A orthogonal, and then they also require that that those vectors to be, so they require the residues vectors, okay, to be mutually orthogonal. So that's why we have different things here. So if you use the Gram-Schmidt, we just require the things to be A orthogonal. But these two people, and then these two mathematicians, they devise the algorithm here, and then they also require that the residues are mutually orthogonal. There's some benefits to do so, but you need to take a look at the proof and the details here. So, but I'm skipping that things. If you take a look at the textbook, and then you know why I'm skipping that part, because it's too long to mention in the class. And so next, let's go to the preconditioning. That is why we talk about the condition number, and then now we go back to the conditional preconditioning. So it's good because you have already finished your homework, and then you know what I'm talking about here, the preconditioning. But for the preconditioning, and then that is the, once again, it's about the homework 2, homework 1, and then question 2. And homework 1, question 2, and I have already extended the deadline to today, the homework 1, and then, but for the question 2, if you are doing the rounding off for the numbers, and then we are using the 2-digit significant numbers there, the 2-digit rounding for the significant digits there, and then we just keep 2 significant digits. And if you are doing correctly,
I have a question about the one above, and the algorithm requires the vectors to be A orthogonal, but it's not also normal, right?
yes, you don't need to be A orthogonal, because a lot of the time we just need the directions. we need the direction, and then we don't need the vectors to be unit vector.
So that the zero now to be all factors that we derive from vectors.
The Gresham matrix, you can simplify the Gresham matrix. You can take away the normalization process, and then in that way, and then you will get A orthogonal sets. Yeah. And but the Gresham matrix, if you take a look at the Gresham matrix, and then the whole process, it will have one step to do the normalizations, and then that's the case you get the A orthonormal. But for the conjugate gradient mappers, you don't need the orthonormal set because we just need the directions. That's it. We don't need the unit vector. So let's go back to the preconditioning. There's some. If you calculate the homework 1, question 2 right, and then you will find out that we talk about the conjugate gradient mappers, and then you would expect that there's some benefits we can get from the conjugate gradient, but from the question 2, you will find out that the Gaussian's elimination, that is the very simple way to we solve the linear system. It's better than the conjugate gradient mappers. So that's the normal one, the conjugate gradient mappers in the gradient mapper in the questions in the question 2. And so we don't expect that, and then but so what can we do? And then you would know what can we do in the question 2C. And then in the question 2C, you are doing some preconditioning, and then that preconditioning is to change the system. So we have the AX equals to V, and then we change the system into A tilde X tilde equals to B tilde by letting the A tilde equals to C inverse A, C inverse transpose. And then we need to choose the C matrix carefully so that we get a good matrix, a good system. And then later on, I would tell you what is the good system. And that is something related to the conditional number. For the B tilde here, we have the C inverse B, and then the X tilde here is just a C transpose X. And then at the end, and then you need to, so I just tell the people who come to my office hour, you can just change the systems to that A tilde X tilde equals to B tilde system, and then solve this system with the conjugate gradient mappers we provided on the algorithm table. And then at the end, with that conjugate gradient algorithm, you will get the X tilde. That's not the end of your answer. You should need to get the C transpose inverse on the left-hand side to get the X value, the X vector. And that is the homework 2, homework question 2. But here, so why do we have the Gaussian eliminations is better than the conjugate gradient mapper here in the question 2? That's because you will find out that if you go to take a look at the conditional number of that A system in the homework 1, I guess, this is my guess, I haven't checked it yet, but I guess that conditional number of the A matrix is not good. So if you are doing some rounding off there, and then it would give you the errors when you are doing the conjugate gradient mappers. And so the error could be propagated when you are doing the iteration in the conjugate gradient mappers. So that's why we have a worse results than the Gaussian eliminations. So if you go back to the theory mentioned in the very first 2 class in the conjugate gradient mappers chapter, and then you would see that we would say, okay, for the conjugate gradient mappers, it can arrive to the exact solutions within n steps. But there's one assumptions on that theorem, and then we assume that the calculation is exact. All the computation is exact, but in the computer you have some rounding off here, and then that's why we have the Gaussian elimination is better than the conjugate Bayesian methods if you are doing some rounding off throughout the process here. So if you go back to take a look at condition number there, and then you will find out that, okay, if you are doing some rounding off here, and then that numbers, the error could be propagated as well. And so here in the question 2, if you take a look at the condition number, I think the condition number for the A is way greater than 1 in the question 2. So what we are going to do is to choose one C to let this number, the condition number of the A tilde to be close to 1. You can check the condition number in the homework 2 question C as well. And let's see, in your question 2C and 2D, and we choose this, we choose the D inverse here. We choose the C and then equals to D 1 over -1/2, and then the D is the diagonal of the A matrix. And if you go back to take a look at the A tilde here, then we will have D 1 over half, and then A, and then D, and then this should be the, I guess, if we are going to take the inverse, and then this should be the 1/2. Am I right here? Yes. This should be a -1/2 again. This one, if you choose the C to be this one, you will see it should be the C inverse. If we choose the C inverse to be the D inverse 1/2, you would expect that these condition numbers for the A tilde is close to 1. Because if we are taking the diagonals of the A, right? And doing the -1/2 here and then -1/2 here, and then if you're just intuitively doing the calculation, and then this is just a diagonal, and then taking the inverse, right? And then multiply by the A. And you will find out that this A tilde, you can expect that the A tilde, the eigenvalue of the A tilde is also close to 1. Are also close to 1. We have, if this is the 3 by 3 matrix here, and you should have the 3 eigenvalues, and then the 3 eigenvalues of the A tilde should also be close to 1. So we have a condition number is close to 1, and then the A tilde, the eigenvalues are also close to 1 as well. You can do some intuitive thought here, but that is not some rigorous proof here. So let's see. I'm going to join the Zoom call here from my computer because I want to show you something. So there's one example from textbook, and that's using the Maple to calculate the things. Oh, okay, good.